Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. Let me adjust this. All right, so sorry about the late start. I just forgot to look at the time while I was eating dinner and stuff. What else was I gonna say? Oh yeah, so also sorry for restarting the stream. It looks like I had some network issues that are now resolved, so that should be fine. Last week I did a stream where I basically just kind of caught up on the progress I made over the summer. And since then, I haven't really touched this stuff except for starting this thing, which we'll talk about in a minute. Had a lot of other stuff to do, which has actually been kind of annoying because I really want to work on this. But I just haven't had the time or energy to a large degree in the last couple weeks. And that happens, and it sucks. Anyway, hi to guys in the chat. Mad Moose, Grachev, Daniel Cullen. So I've been talking mostly about the rasterizer because that's mostly what I've been working on. But of course, in the back of my head, I've also had a couple of the other rendering related workloads that we need to deal with in this system. And there are primarily two because we're doing a tiled renderer. There is tile binning, which I still don't have a complete solution for, but I'll continue thinking about that. And vertex TNL. TNL stands for transformation and lighting. I don't know if that's even a term that's really used anymore, because now with the advent of programmable shaders that we've had for the past 15 years or so in commodity hardware, shaders can sometimes do a bit more than that, I guess. But for this era of hardware, those are the two things that you would use this kind of thing for. Yeah, exactly. That term was really hot in the 90s, which is appropriate, right? That's what we're doing here. So, anyway, so I started thinking about how am I going to accelerate this? I know this is a bit of a tangent, but I thought let's just say that I thought I would maybe continue just on this design, which is just kind of putting together how I want to accelerate this, which may not be this, but this is just what I'm thinking now. And also maybe I'll do a bit more documentation on the pixel pipeline, just because I kind of feel like doing that, and we'll have to see. Anyway, so what this is an untitled hardware block that I'm thinking about, and this is mainly to accelerate TNL. So if you look at transform and lighting, I actually don't have any lighting set up in any of my tests here. Let me pull up a proper terminal. Dev projects xenowing, misc struggle, cargo run, release, -- sim. And let's see what we get. I don't think it'll build too much, but we'll see. How long until you can render Lego Island? That'll probably be a while. All right, so this is a low-res sim, but this is, the graphics hardware. Actually drawing some really crap scaled rectangles for test content. Yeah, so in this setup, there's no lighting. I've been kind of ignoring that part of the workload, and I kind of think I should maybe add that soon in order to actually approximate this stuff. And I'll probably go for something that's I don't really need it to be fixed function because this is going to be part of the TNL workload, and the rasterizer is just going to accept a color. So I think that's probably not going to be something that the hardware really knows about, actually. So it's probably just going to be really basic lighting, and even just per vertex. Yeah, not very focused today, whatever. But yeah, it would be kind of like basic vertex shaders, really. I could also make a unit where I just take the exact features that I want for TNL, and I put all those in a pipeline like I've done with the pixel pipe, but the reason I'm not doing that is honestly because it just sounds more fun to make something somewhat programmable. And I don't think we need much. So if we look at a bit of this workload, this is in the test setup, this is the transformation. And again, I've ignored lighting, and I want to fix that. But what you can see here is we take the original position And we just multiply it by this model view matrix and then multiply that by this projection matrix. And this could mathematically just be, I could have multiplied these matrices before and just done one matrix multiplication here instead, which would obviously be faster. But the reason I didn't do that is because I was thinking about doing lighting, and you would typically do that in view space. So I was thinking to add lighting calculations there, but I haven't done it. But if you look at this, this is literally just a matrix and a vector product and another matrix and a vector product. And this matrix is 4 by 4, so is this one, and then these are 4 component vectors. And actually, this model view matrix, a typical model view matrix doesn't actually use the last row of the matrix. It's just constant, 0, 0, 0, 1. So it essentially just propagates the W value, assuming that that's actually 1. And so I'm thinking I probably want to try and take advantage of that. So for this part of the transformation, if possible, you would only do 3 of the 4 dot products that composes a matrix matrix vector multiplication. Whereas here you need to do 4. And I mean, if you were to take like a fast path, like let's say you had a path that didn't do any lighting, then again, you would multiply these beforehand, and then you would just do a single matrix multiplication. Then you're basically just doing this step, and then you save a lot of work there. But I feel like it's going to be common to have some kind of lighting built into this pipeline. And in that case, you'd want to do this, and you'd want to do it faster, and then you'll get a 3 component vector out. And then you want to do some kind of dot product with that. And you also want to transform the normal with this matrix. Or actually even a smaller version of this matrix, because you wouldn't do the transform component. So then you would do dot product there, and then you'd have basic Lambertian diffuse. Is that how you say it? Lambertian? Lambert diffuse. Let's go with that. And maybe even with a lookup table, you can have more fancy lighting models. And maybe that's something I want to support. That'd be kind of cool. I didn't plan on dealing with sRGB, but the Voodoo did that again with lookup table, I think. So it would actually be pretty cheap to do that. Maybe I'll just do that. At least that sounds relatively easy to implement if I do it that way. Hadn't considered it, but now I'm kind of thinking that that'd be a cool idea. We'll see if I remember. But yeah, you said this smells like the PS2 vector unit, totally, and it's definitely inspired by the Sega Saturn one. So what I'm thinking is, if you look at this, there's this would be 3 dot products basically. This would be 4 dot products. The lighting itself would be a couple dot products plus like some max like clamp stuff. And maybe there would be Phong lighting. Again, I'd probably do that as the lookup table. And then I'd probably add some additive color component to the rasterizer as well, in addition to the like multiplicative color. So yeah. Yeah, and I guess then if you did sRGB, you could just store everything in sRGB internally, and then like your blending and stuff would do that too. A downside, however, is that you wouldn't get as good precision if you're just using 8 bits. Like your distribute, or rather, I guess you could store an sRGB and then do that remapping as well on the inputs and outputs, but I don't know. Maybe that's kind of worth doing too. We'll have to see. But yeah, this whole thing can basically be factored as a lot of dot products plus a few more things, not actually that much more. And that's kind of exciting. So I was thinking about ways to accelerate that, and I came up with this, which is literally a dot product engine. So I started with this middle part, which is like the core, or I guess this bottom left part. And so, yeah, I could do everything in linear and store it linear. But again, then you don't have as good a precision, because if you're just using like linear 8 bits, then you lose precision in the darks. Whereas I think if you actually store with sRGB, you have that remapping that preserves some of the detail where your eye is more sensitive. I think it's in the darks, right? Maybe it's in the lighter ones, but I think it's in the darker ones. Linear 16-bit I won't do, because it increases the bandwidth requirements. I guess that's why there's the kappa. But it's something to think about. I totally hadn't thought about that, so I'm glad you brought it up. But yeah, so this is what I'm thinking is like a dot product engine, and this is not finished. And in fact, there's a couple errors here that I want to address. But yeah, if you're gonna do so, this in particular, it's not just dot products, but it's also the shape of these is important, right? Because this is assuming this is the first 3 rows of the 4x4 matrix and a 4-component vector in. I mean, really, it'd be like a 3-component vector in, but whatever. If you did it that way, this is 3 dot products with each with 4-component vectors, and this is 4 dot products with 4-component vectors. The lighting's 3-component vector dot products, but that's fine. So I thought about what about doing that like a pipeline just for doing dot products. And so here I have like this A register, which is one of the inputs to these multipliers. B register is another input to these multipliers, and each of these would be like 128 bits wide. So you have 32 bits per component. And on the output of that, these actually all should be 64 bits wide. So you'll have some expansion. And I could either like truncate that, like just pull out the middle bits, for example, because that would give you, like if you put 16.16 fixed point in, because I'm probably going to do all this with fixed point. If you do 16.16 in, 16.16 in, you'll get 32.32, but then you can just take the middle bits, and you'll get 16.16 again, which maybe is worth it. Probably not. Probably not what I want. Or is it the middle bits, or is it the upper bits that you get for that? Maybe it's actually the upper bits. I think it's the middle bits. And then, anyway, I think I'm actually going to just make these wider. And so then this is actually a 256-bit register, and then I want to do these horizontal summing of these individual components in 64-bit as well. And then I think I might actually want a shift here. So you're always going to output 32 bits, a single 32-bit component. But then you might be able to select which bits you want. Yeah, I could try to do it in floats. All my tests use floats currently, but I really want to try and do this in fixed precision. By the way, hi, Alkama. And thanks again for the sub. I really appreciate that. So we'll have to see. I'm being stubborn about doing this in fixed point. One, because I want to try to do this workload that way. And if it becomes too hard, then I can give up and try to implement floats. But the other reason is that I don't want to implement floats in the hardware. So we'll have to see. But yeah, anyway, I want these sums to be in 64-bit, and then I want to have some kind of shifter on the output. So you always output 32 bits. So with this whole thing would be a pipeline. So every cycle you need to read in 128 new bits. And so that's why I've added like 2 data memories. I think since a lot of this is dual ported on the FPGA, I think I could actually get away with 1, but I think I'm going to logically have 2 anyway. So each cycle you would have to pull a value from each, 128 bits value for each. And then you would store back a 32-bit to one of them. So typically you'd have like the matrix in one of these and then all the vectors that you're operating on in the other one. And every cycle you'll pipe in whatever row of the matrix that you're multiplying with alongside whatever vector you're multiplying. In fact, I think you would actually less often pull in the vector you're multiplying and just reload that a few times so you put in the different rows of the matrix. And then you'll pipeline this. And so every cycle, if you keep this saturated, you're going to produce one component. And I like that flow because then for the case where you're only doing, 3 dot products for a 4x3 by 4 component vector matrix, then you're going to be able to produce the result of that multiplication in 3 cycles. Whereas if you're doing it with 4, then you have 4 cycles. So it kind of scales with what you're doing there, which is nice. Whereas if I did like 4 multiply accumulate units, then I would get a lot worse utilization for the cases where I need to only do 3 dot products. Because then you do the dot products kind of sideways. if you were to do a pipeline that way. So I actually think doing a dot product engine it feels kind of weird to do it this way, compared to like a more generic kind of DSP flow. But I just think that this is actually really applicable, and I think this hardware would be relatively easy to make. So to control this pipeline, I'm thinking that a user would have a separate CPU, and you, via the system bus and memory mapped IO, you'd load up a bunch of the data memory, and you'd load up a bunch of code for this unit. And the code, I'm thinking to have it as like some kind of either just very long instruction word where everything is already decoded, or have a very simple encoding scheme and then like a decode stage here. They'd probably only take like one cycle or something. And I'm not entirely sure what the instructions are going to look like, which is why I just wrote sequencer here. I need to figure that out and start with like a software model. But yeah, I'm essentially thinking that these are going to be very basic and just have like the individual bits of the instruction kind of say where these are going to come from. So I don't know if it's quite clear in this picture, but this thick line, this is meant to basically be like some kind of crossbar where you have each one of these has like a read and write port, each one of these memories, and these have two inputs. This has an output and an output here. Oh, and by the way, I might remove this output if I have a shifter stage, and I might make it possible to bypass these and go straight to the shifter. So you could potentially output the shifted result straight from the products. So you'd have like a component-wise, well, they need a component-wise shift, or serial only need one. Yeah, maybe I won't do that. I'm not sure. But yeah. Basically each of these, like, so there would be an input to this register, and this could come from either one of the memories, for example, right? So there needs to be a mux there, and same with here. And then on the right ports of these, there's going to be a mux each where they can pull from. Well, I guess if I remove this, then there's only going to be one output from there. So you'd have that, and then you'd have all the enable signals for those read or write ports, and all of that would be part of the currently executing instruction, I think. So the instructions are very low level in this sense, but at the same time, I think that makes this really controllable, and should make it really efficient. Like other ways I could have accelerated this workload perhaps are to add some SIMD processing into the CPU, or maybe even an engine like this into the CPU. But I really want to be able to keep this fed all the time. So I think a dedicated unit that can definitely keep up that pace is going to be really helpful and relatively easy to design. So, because I think it's basically this, and then how do I design the instructions in the sequencer? Now, one thing that the sequencer is going to need is some kind of loop support. And I'm not entirely sure how I want to express that yet. Like all these mux values and stuff, there's going to be essentially an instruction register that's loaded every cycle, and then all these mux inputs and everything are just going to be read straight from that. So data will flow through this basically all the time anyway, but it's mostly going to be crop data. And then you just have enable signals for all these different parts that are driven by the sequencer. And the sequencer ideally, again, is going to be executing one of these instructions every cycle. But yeah, for loop support, I want to have loop support built into this, I think. Maybe that'll be part of the instructions where they'll have some kind of conditional branch. And I don't know what the condition is going to be. Maybe I'll add a couple like internal counter registers, which I'll probably need, because for the addresses for these read and write ports, you need some kind of way to like increment those or reset those or set those to a specific thing and then increment them. So we need instruction support for that. But yeah, I'm not really sure. So there's a couple things I need to do with this. I need to, first of all, like look at this workload and kind of extract values and see if I can kind of do that naturally with this kind of engine. And I might even, for the first like software prototype, just plug it into here and even just do it with floats. Just that way I don't have to do as much stuff. And then I can start working on getting it to be fixed point or not. Like I can kind of, I guess, separate the design of this from whether or not it's going to be fixed point or not. The thing is, if it's going to be fixed point, I think a lot of the stuff is going to be faster. If it's floats, I think then this pipeline ultimately will have more latency, which I'm not too concerned about, because again, the point of having this kind of sequencer is that you'd be able to keep this pipeline basically completely saturated, which I think is possible, right? Because you could, for example, pipe in the vertex transformation, and then as that's going through these last stages, then you would pipe in the lighting for the same vertex. So all the different calculations that you need for that. Or maybe you could do like the inputs to the lighting first, and then you would do the positions, and then you could do the actual lighting calculation with those inputs after. And then that's what you would do for that vertex, but then you would also pipeline like the next vertex in there as well. So I need to think about all that, and it's not that clear in my head other than just like, yeah, this should be scheduled. It should be possible to schedule this that way. But all the details about like what registers there's going to be and what the instructions look like, I find it very difficult to like foresee how that's going to look until I start writing the code. So that's why it's a bit unclear in the diagram, because it's just not clear in my head yet, but I think it will be. Oh, that's interesting, actually. The PS2 VUs do dual issue. The lower pipe is integer stuff while the upper is more math. Maybe I could look at that. Because I've seen that a couple other places, that kind of dual issue where you do integer stuff in one pipe and float in the other. But I want to find more examples of that. Maybe that's a really good idea, because then I think the N64 vector unit does that too, where they basically took a MIPS CPU that's similar to the main CPU, and they added a SIMD unit on the side of it. So I think that might be a good idea, because exactly, yeah, you'd have counting and loops and some logic and everything there. And ideally you keep this pipeline saturated the whole time. That's kind of the thing. And again, I want these instructions to be very low level. Like I want scheduling and everything to basically be done in software, which might make this instruction memory a little bit larger, but I don't think that's going to be an issue. So yeah, you DMA into here, you DMA instructions into here, like the microcode in N64 parlance, and then you'd DMA your working set into here and maybe your matrix into here, and then you would have your output that you would DMA out of after you do this. Because there also needs to be like a register interface where you can check like on the status of the engine. I've been thinking about calling this the dot product engine, DPE, because I think that's kind of cool. I'm not sure. But yeah, I just threw this together the other night. Was it last night, maybe? I don't remember. I think this makes a lot of sense, but there needs to definitely be some additional work here. Oh yeah, and the VU has a separate pipe for divs so they can run while you have moles and such running. They take fixed 7 cycles. Yeah, that's kind of a cool idea too, because if there's another reason why I want to do dot products that I need to think about, and that's primitive assembly. So right now, this is not necessarily the best way to factor this, but it's the simplest way to factor this is you have all this interpolation stuff, or not really interpolation, but like you get the edge, these edge functions from, or yeah, you get these edge function values and the edge function partial derivatives while you're doing triangle setup. And the way you set up the partial derivatives for all the other components is you do dot products. So you take these 3 edge function values and you dot those with the individual components here. And it might actually be a nice way to speed up this part of the workload as well. There's other ways to do this, like you can, instead of factoring this as a dot product, you can factor it as, you would do, I think instead of, because this is, 3 multiplies and 2 adds, which again, if you have a dot product engine, is kind of the thing, that's kind of how you want to factor things. But if you're worried about, for example, the multiplies, I think you can do this where you calculate like the first value, or you take this first value and then you add this minus this and multiply by this minus this or something. Like you basically factor it into 2 subtractions, 2 multiplies, and an add or something, and 2 adds. Yeah, and that's the other thing. You're totally right about that, Daniel. So I'm thinking that maybe it would make sense to have some kind of approximate reciprocal or divide support as well. So maybe it would make sense, in addition to this, to have a divide pipe that also would have that kind of fixed latency, and then you'd have to schedule that in the code too, which I think is actually pretty attractive for this kind of unit. So I think that's a good idea. But then suddenly this workload, which I was thinking the whole time that I was just going to have to refactor later, I was thinking maybe I don't have to do that. Maybe I should just design my T&L unit to do T&L and assembly, and just work with dot products everywhere. Maybe that's a good way to do it. I don't know if it's a good way to do it. I don't think I've ever seen that before. It just sounded fun in my head, and I think I'm going to go for it. I can think of a lot of worse ways to do it. Let's put it that way. Like soft floats on the CPU, for example. So I think getting the software together for this unit is going to be somewhat of a challenge, but I think it sounds like kind of a fun challenge. And I just kind of like the idea of having this as hardware. So I think I still need to think about this more and kind of flesh out the details, of course, but I think I'll implement something like this. That sounds fun. So maybe I can actually just save this. I'm wondering if I should, let's see. Yeah, I should check out that PS2 doc, shouldn't I? Right, so yeah, clipping too, like I'm just kind of ignoring to a large degree, but that's definitely part of the primitive assembly, I think. Or it's part of the pipeline before that, really. But if I have a unit to do primitive assembly, it should also do that, I'd imagine. So I think that makes sense. Yeah, I can show you the clipping code I have now. It's just this. If any of the z coordinates of the triangle are out of here, then abort and let the guard band handle it. And I'll probably stick with that for a long time. Anyway, I think I'm actually going to stick this document in the xenowing docs. I hope that saved it with the right extension, because sometimes it doesn't. Also, I keep forgetting that Draw.io has renamed itself to diagrams.net. I don't know why. I'm also going to export it as SVG. Oh. Keep flashing my desktop. There's nothing on there. Let's see. xenowing doc. Save that there. Just going to take a peek at that as well. Yeah. I think I'm also, though, I'm on a branch, yeah, this read cache branch. I think I'm going to check out master and do some docs on there and then rebase that branch. Do I have, oh, there it is. Yeah, good. That. Yeah, I like this idea. In the meantime, I would actually like to also do a diagram for the pixel pipe, because I pretty much have that working now, and I don't think it's going to change much. So let's just kind of document that. Let's see, this is the color thrust in RTL. I will also eventually do a diagram of like how hold on, of how the different parts of the GPU are going to fit together. But I'm not too worried about that yet. And that's going to change as I add like texture caches and stuff. I still need to figure that out. So I'll probably do some diagrams before I do that, but maybe I'll do it after. This project, like the order in which I'm doing things is just kind of all over the place. But that's kind of the nice part when you do free time projects is you're not on any schedule, so you can kind of just jump to whatever's the most fun at a given moment, and that's totally fine. And I think that's also important because then you have more fun. Which is the whole point. But I think the Voodoo docs, I want to look at that because they have a diagram that I kind of want to do something like it. Like this. No, that's not the one. I've thought about seeing if I can make like this kind of PDF doc as well, just with some of these diagrams that I'm making anyway. So I don't think this stuff would be too hard to generate. I could use something like LaTeX, but I think there might be better options for specifically doing documentation. Here we go. All right, I'm gonna what was that? I'm gonna zoom out a little bit, so you won't be able to read all of it, but you can see the important parts, right? So there's like a color 1 here, color 0. And the point is that there's all these muxes. So this doesn't describe any kind of timing of this pipeline at all, but that's not the point. This describes how the actual pipeline is laid out and how different parts fit together. I think this is the right one. Yeah. So I kind of want to have this kind of documentation for the pixel pipe in the color thrust as well. I think it's just a good idea to document that. But it is simpler than this. This even has chroma key. I keep forgetting that this chip had features for that, which is rad. And a mux for the alpha. And then you could flip that with this reverse blend option. Oh, they do +1 here. That seems wrong to me. Because then you could never accurately have 0. Unless we're just adding a 0 bit, but I don't know. Sign bubbles that multiply, clamp, add color here. Yeah, and I guess you can bypass all of this. That's what this is trying to say. These aren't very pretty diagrams, I'll admit, but I think they're extremely useful for understanding the different options in the pipeline. So I think I want to do that. Let's see. So I guess if this is just the pixel pipe. What did I call that? I think I just called it pixel pipe. Color thrust has more than that because there's some additional control logic here in the GPU, which isn't much. It's basically a register interface, like ports for all the memories and all the organization there. And it's also the interpolants, which is basically generating the inputs to the pixel pipe, and some logic for controlling some scheduling of when these happen. And each interpolant has a min and then the partial derivatives in x and y. And then I've also added these like mirror values for these derivatives. And the idea there is that whenever you tell the GPU to start, these mirror values are going to get copied over from like the actual value, and then the mirrors are going to be used in the actual interpolation. And the idea there is that while the thing is actually rasterizing, you can change all these registers So you're basically queuing up the next work so that when it finishes, then you can kick it off again. And it was just really easy to do that in the RTL. And in fact, for the min values, I already had that because I the way I do the interpolation is the interpolators actually are always running. So it's almost as if it's always just sitting there looping through the whole tile all the time. It just never enables like reading or writing. And then when you click start, it resets all the counters and everything, and then just keeps going from there. So that just made it logically really simple to have it do that. And then I realized it was useful to also do that for these dx and dy values just by adding another couple registers. So I think that was a good choice. Although maybe if I never end up using that, then what I should rather do is just get rid of these for to save space, because they're not strictly necessary. It would make the code a little bit simpler too. But yeah, these are kind of like, these are the like configuration signals. There's not that many. In fact, these are really the ones. Depth test enable, depth right mask enable, filter select. Oh yeah, that's like nearest or bilinear. And then you have blend, source, and depth factors. And all of these basically translate to mux controls. And then, yeah, these are all the interpolant inputs to the pixel pipe. And then there's also these additional control signals that go through the pipe and are all like delayed through the pipe as well. So you have whether or not the input data is actually valid, which that's another thing that happens. So when you tell the GPU to start, then it starts piping a bunch of valid ones in there. Otherwise, the ones where they're just interpolating all the time, they just keep piping 0 down this part of the pipe. And then the pixel pipe will know that it's like active until it sees something where the valid bit and the last bit are both set. So the input generator will generate this last bit here, and it actually generates this whenever it's at the end of the tile, not even if it's necessarily valid. But again, that's to simplify this logic. So the idea is that when you kick off the GPU, it will set like the input generator is active and then the pixel pipe is active, and then it will clear the input generator bit once that's done generating inputs, and then it will clear the pipeline active bit once this valid and last inputs for the last pixel go through. And the reason why I did that is because then you know if either part is active, and you can OR that signal, and then you know the GPU is active, because you don't want to start sending in new data while it's still processing the old data. I think actually, due to the way that this renderer works, and the fact that there's enough latency in the pipe, I think it's actually pretty much always safe to start generating new primitives into the pipe. So I may actually want to do that. So you could essentially have a little bit of parallelism when you're processing primitives as well, because they won't touch conflicting pixels. So that might be something that's actually worthwhile. But you don't want to, for example, pull the tile memory out of the data while the pipeline's still running just because the input generator is still generating inputs. So you definitely need to keep track of both kind of active states. And I guess that would also make this logic a bit more complicated, because then you would need to do, I guess instead of this, I could have like a counter. So you could have a certain number of primitives in flight, and then whenever you put in a new one, it would increment that counter. And then when you have this valid last thing, it would decrement that counter. And then the pixel pipe would always be active until that counter is 0, rather than until this condition happens. Whatever. Future thoughts. But yeah, I think we should just make this diagram, and I'm going to work from the bottom up, I think, because that's probably the easiest to do. So yeah, I just want to document the pixel pipe right now. And let's go to the end. It ends up being a fair amount of code, but I think this is, well, probably not the most readable. I actually thought about, I think I mentioned this before, I thought about actually making like a little DSL just for describing which values I need, and then how many cycles of delay they need kind of internally. So you would describe like a signal, and then sometimes you would insert registers into that signal just to like delay stuff. But but then you would just say like, okay, the previous color is going to be this read that I issue from this buffer. And then it would kind of go from the last one to the first one, just work backwards in those signals and kind of figure out how many cycles there actually needs to be in the pipeline, and then insert all the registers and everything for you. I thought that would make a lot of this code a bit simpler. I may still do that because I can, and it sounds kind of cool. But in the meantime, I've just basically unrolled everything. So you can see I have these comments and then all this stuff for the stage, which just takes whatever the last, like, so this like R for at this stage, it's literally just propagating a lot of these values until it gets to the end. And it's a lot of that boilerplate that I think I could get rid of, while also avoiding potential errors if I don't propagate something correctly. But I just kind of did it the unrolled way first, and it works. So maybe I'll change it to make it cleaner. Maybe I won't, because it works. It's one of those things. Anyway, let's see. I can start with these, really. I think it's useful to even document some of these outputs here. So I don't really know how this is going to look yet, but we'll just start somewhere. Stuff like this, where we do top. Nope. Really? Is that not top? Oh, it is. There's just some spacing there. Let's start with something like this. I don't know how detailed I want to make this, but again, we'll just start somewhere, see what we get. So ultimately, these are the outputs of the pixel pipe. Like, there's really not much more than this. I mean, there's like word enables and stuff, but that's more of a detail of the memory organization. I think and same with the addresses. Like, if we just look at what there is for a single pixel, this is it. This is what we output. So yeah. So then how are these different values determined? That's really what we're trying to document here. I think this is just output, so it's all determined by the time we enter this stage. Well, no, prev depth is here. It's actually here. There's the depth test result. And then that's used to enable these writes. That's what's happening there. That makes sense. So I think I'm actually going to do it like this, where I just do it really low level like this. So it's basically like this too, is also low level with like ors and muxes and stuff like that. Small ALUs. And then, yeah. Maybe I'll add those little ticks that specify like the width of some of these values too. Something like this. That's really big, isn't it? It is. How do I change the grid? Is it file? Page setup, maybe? Yeah, it is. 5. Yeah, there we go. Sorry if this is like painfully dull, you guys, but I just think it's really useful. Actually, these are 32 by the time they go out. Also, the alignment here is different, I guess, like that. Yeah, I like that. And I think also I enabled all of these, so I should be able to see like ands and ors and stuff. Check that out. So rotate this. I should be able to make this look a little nicer, I hope. Stop snapping to stuff. I don't want it to do that. Okay, not super happy about this snapping. Is there a way to do that? Control Shift maybe? Oh, that's... I'm learning some cool shortcuts here, but they're not the ones I want. Okay, so maybe Alt is actually what I want. This is a really dumb thing to like sit here and optimize the look of these muxes, but or the look of these components, but deal with it. All right, good enough. It looks something like that. Cool. So this really I want to name this like the depth test. So depth for output enable is going to be this. And then this text here, which I'll add is the depth test result. And actually, that's not where this goes, right? Because this is the depth test result is one of the inputs here, and the other one is this valid signal. Maybe we don't care about the valid signal because I actually don't think that's useful for like users. But the edge test, that is useful for. So is this aligned well? Just to be sure. I'll do that so I definitely know that it aligns well enough. Cool. This result, and then we're going to have another line here, which is going to be the edge test. And I think this one... Oops. Oh, I can just snap to that. Yeah, whatever. You know, I think also this is a detail, right? Because, oops, I don't want to delete that because, oh, I'm going to use that, but. Yeah, I think it actually makes sense to omit this edge test as well, because the edge test is whether or not you're inside the triangle, and then like the valid is a... Like these are invisible to users. What you care about is what happens for pixels that are within the triangle, right? So I think it makes sense to list this, but these are more like implementation details. So then the depth test is this, right? You have the previous depth and then whether or not depth test is enabled. So it makes sense to have, you know, a depth test enable signal. And it makes sense to have a previous depth. And the previous depth is 16 bits, I think, is what I decided. And then you also have the depth, which I'm calling Z. So a bit inconsistent there. I don't really care about it. So then you have less than. I don't know what the best way to describe that is. Maybe one of these. I think these are adds in this diagram. Yeah, sorry about the ads, you guys. Whatever. Eight and 9, so you have 10 here, and here you had 8 and 9 here. 1.8, 8. Yeah, I think these are supposed to be adds in this diagram. But I want like a less than. Does it even list that here for that? Maybe not. I mean, you don't really need to, but I want to have it on here, so. Yeah, because this is also per color component, I guess. Yeah, whatever. I'm going to have it here. So then we need some way to describe this less than. And I had, I guess, what are these? Oh, stuff like that. You can have flip-flops and everything. Fun times. I'm definitely going to use this in this diagram at some point. And a little inverter. Cool. Switches relays, I think, had some useful stuff in there. Maybe not. Is it MISC? Yeah, I'm looking for it because I thought there's muxes. Maybe there's no like ALU kind of thing. I could use like one of these function boxes or something. It really doesn't matter what I make it as long as I make it understandable. So even just a box with a less than symbol in it's probably good enough. Let's be honest. Or a cloud. I like using clouds for logic. I've seen a bunch of diagrams where these are used for like combinational logic. I think I kind of like these. So as you can see, I only have less than, which I think is fine. Maybe I'll support more later. See something like this. Do this. Right, so if you have this, then you have the depth test result. Just going to shorten all these up. I have no idea if this diagram is going to look good in the end, but whatever. So this is this or not depth test enable. Was this an and? This is an and. What or? just going to make it match this more or less. We don't need this to be. Oh, why didn't that rotate? Thinking something like this is probably good enough. Something like that. Then this is your depth test result. Whoops. And kind of an important thing. These are both the same, I think. Just a double check. I'm pretty sure these are the same. Ooh, actually, this one also has another and in there, which is if the right mask is enabled. That makes sense, doesn't it? Oops, I did that again. Yeah, something like this. And then we can split this off here. Let's just do that even. And then we can bring this up here. Yeah. So this is how this stuff is determined. Maybe I don't need this to be so long. I can put this over here. Yeah. And maybe for these, like previous depth and stuff, I can do something like this. Because these also like, oops. Really, did I snap that there? Not me to do that. Something like that. Yeah, this is basically the whole path for the depth. That's how I've described that, which is pretty good. Okay. All right, so color is determined here. And this is where things get definitely more complicated. Right, because this is clamping. That's definitely the first thing that happens. Oh, Kami, you're not sick. You're a genius and you're inspired, and you should definitely do that. Emulators are cool. I fully support that choice. Maybe I should call this like less than. Sanity is relative. It definitely is. I think with an emulator, especially, you can choose a system where you have like a lot of specifically designed test ROMs. Like I know Blarg did a bunch of ROMs for Game Boy. So I think Vectrex is like the weirdest. So in a way that might be one of the more fun ones, but I think GB is probably the most accessible. And a lot of people would say, "Oh, do chip 8 first," but I don't think you need to. I think it's fine, but I think it's fine to skip chip 8. I didn't know NES had a lot of testing ROMs, but I guess it probably does. Yeah, and you can get a lot of the software running without getting timing and stuff like perfect. Like C64, for example, does not have that property. Amiga does not have that property. I don't think there's many Game Boy games and demos that really are that strict with the hardware, for example. I mean, I found an emulator bug when I did my Game Boy demo, like, 8 years ago now. That's insane. Anyway, but that was actually because I wrote the code wrong and triggered the wrong interrupts, and the interrupt I triggered wasn't triggered very often in normal games, and it happened to have a bug. So the demo itself normally doesn't require, like, as I meant it, didn't require that difficult timing anyway, so yeah. I don't know. I support that decision. I think Game Boy or NES would be great. Yeah, exactly. It's a feature. At some point, I still would like to use the testing setup I made for Virtual Boy and dig into some timing stuff there. But we'll have to see how feasible that stuff is. Anyway, for colors. Also, yeah, this is 16. I'm going to do this too, actually, because we need to output the depth as well, don't we? Okay, we're going to do this. Move a lot of this stuff just like barely. No. How about this? Yeah. Now we're talking. Making these diagrams is so tedious, but this is by far my favorite software for doing it. Of all the alternatives I've tried. Which admittedly isn't that many, but of all the ones I tried, this is easily my favorite. And I think I want, when I branch like this, I think I want that to be marked. Probably don't need it, but I think it's going to help. I don't know the best way to do that. Is there like an endpoint I could do? Like this maybe? That's dots. Oh yeah, something like this would be perfect, right? Because I put a dot at the end. That's a big dot. Maybe there's a smaller dot. Yeah, I think I'll actually do none there and add a dot. I think that's probably better. So then maybe just a circle. I can scale down a lot. No. Oops. Page setup. Can I do 2.5? No, I can't even do that. Oh no. All I want to do is make a dot. There has to be a way to do this nicely. Maybe that first way I found was the best way. But I wish I could change this. Maybe I can? Yeah, that'll work. Yeah, I like that. Great. By the way, I'm going to save this while I'm working on it. I call it color thrust. I'm actually going to rename that. Pixel pipe. Because this won't have the rest of the GPU. Oh yeah. I meant to move this over too, didn't I? Cool. Also, earlier today, kind of unrelated, but I was totally thinking about what it would be like to write a Wolfenstein or Doom like Raycaster on Virtual Boy. Because Virtual Boy has these affine backgrounds that I think you could use that are kind of like Mode 7 on the SNES, but you have more of them. You could use that for like the floor and ceiling and get everything perfect. And that would be like done by the hardware. And the frame buffer is actually organized sideways in memory to help the scan out for the display. So if you were doing like a Raycaster and drawing the walls as like vertical strips, it's suddenly more efficient to do them as horizontal strips, which I think could be cool. Because instead of doing like read, modify, write for every pixel, you could basically just write out all the pixels, which should work pretty well. I guess you would do that too normally. But no, since it's a few bit planes, I think you have to do that. So yeah, so you'd kind of like batch up the writes and then just write them all out. So I think that would be really natural for that system. But the CPU is slow, and that's a big disadvantage. And also, you'd have to draw the frame twice, which could be a cool effect because you'll have the stereoscopic effect. So you'd actually, the walls would be projected slightly different, and so it would look like, I think it would get a really good effect. But I think it'd be really slow, even if you did it like with the hardware in mind. Although I guess depending on how you do it, because you have these bit string ops, which are kind of like a poor man's blitter. And I guess people have used that to like fill polygons. And I guess you could maybe do something like that for the walls. But I don't know. I don't think you'd be able to support textures very nicely that way. Anyway, that's way off topic. So I'm not really sure what the best way to do like per component stuff is, because it actually changes. I mean, really the only difference is that I have alpha is kind of a separate thing, whereas red, green, and blue do like additive blending. I guess alpha could too, but it doesn't really make much sense to me to additive blend the alpha part. Maybe it does. I don't know. Maybe I just did this wrong, but it's up to me, so it's not wrong. Ha! Gotcha. Take that, me, from 2 seconds ago. Yeah, no, oh yeah, I mux like the source factor from other stuff here. So I have 0, 1, source alpha, and then 1 minus source alpha. Those are my options for source and des factor are the same. Yeah, because I have the previous color here too. Multiplies those out. Add and clamp. What? How is that happening? What? Center. Okay. Taking that from the other dock. Because this also has some extra bits in it, the way I have this organized. I think I have 9 bits here. No, I actually have 10. It's interesting that this one does too. I wonder if it's for similar reasons. I don't remember. I think it's just because I have 2 adds in the pipe, and I guess it's the same for the Voodoo one. If they do an add here and an add here, then you end up with basically 2 extra upper bits. And I use that for the clamping logic, which I don't really want to write out. I basically check if either the upper bits, or if both of the upper bits are 0, then you take the actual bits. Otherwise, you just dump a 255. That's how you check that. Easy. And I run that for each of these. I think I want to like do something like this. And like have like a box around this to like denote that this is like per component. Something like this, and I can fill out the rest of the box after. Oh yeah, just hit it there, whatever. And so then out of this, you'd have like some kind of concat here, you know, for all the different components. And then out of this, you would get, whoops. I don't know what feature that was. Probably useful. Really? Yeah, whatever. And so then this would have this output here. It's going to be 24 bits wide. And I think this is actually just going to be a regular line, isn't it? No, regular one. Snap where I want, please. If you're polite to the tools, they'll do what you want. Hey, Artemis. Basically like this, and then we copy this over too. This is 8. And really, if I wanted to have the bit depths or the bit positions correct, I would move this over here. So I think I'll do that. This. This, and we can do something like this. Nope, move it. There we go. And then I can pipe these into here. I feel like sometimes these don't quite snap how I want. And I haven't really figured out a good way to make sure they always do that. Almost got it there. Yeah, good enough. I think it would look better if they were there. It does, slightly better. Look at that. Can do this so that I'll have space enough for this line that I want. And have this. 8. So I'm trying to denote that this whole pipeline here, this area of the diagram, is going to represent each individual component. And then I kind of want to compress this slightly. And then all of that is concatenated together, to form this pixel output. This here. I think this is getting to be clear enough, I guess. I feel like I can squash this down a bit too. To match the other side a bit. I get really anal about some of these alignments and stuff, which is annoying, but it's fine. So that's this part. You just call this A at this point. Here it should be. I just know I'm gonna want more space here. Also, I know too that I'm gonna have I like too how they like labeled this. This would be 1.8. And I know I'm gonna have, I think I have this like this, and this is actually, what is it? I think it's cat A. Oh, is A 9 bits here? It must be. Came from here, which is the previous one. That come from the input? So these are definitely 10. This must be 10 here too, but this only adds one more bit. So why is the alpha 9 bits before that? Yeah, it's a lot of lets, isn't it? It's from here. So where's this A come from? It's this one. Oh yeah, this part. It's definitely it. So A here. A and 1 minus A. It's definitely 9 bits by the time it reaches this. Although I'm not sure when that's determined, I guess. Oh yeah, it's this scale comp thing here. This makes it 9. That's what it is. Yeah, exactly, 2 curves. This is a fixed function pixel pipeline. So it already works, but I'm trying to document it and remember what I did, which is why I'm documenting it. So I've done the depth part, and now I'm doing the color part, which is a lot more complicated. But yeah, these inputs are actually 10, 2.8. I might move them over on this side. I really want it there. That's what they are. Yeah, so here, somehow the signal becomes 10 bits. And I think that's literally just because I take a 9-bit signal and I add 0 to it. Not sure what the best way to describe that is yet. So I'll stick a to-do here. Can I make these red? Get a big stupid bright red. I'll even do that. That's actually probably the best to-do color. Yeah, so this is adding red, or the comp, to the previous comp. And these sums are... yeah, they're 10 bits here. So this is where we want the add. So let's copy one of these. Oh, you mean like a shuffle two curves? Or... hey, Dark Second. Thanks for the sub. I think that kind of thing is common for components in SIMD, but I don't think those go down to bits. Maybe there's a machine learning processor that's doing that. Because there's a lot of research going into reducing bit widths for everything, and just doing a lot of things stochastically in that space. So I could imagine there being like 1-bit activations, and there's some accelerator somewhere for that, and maybe you would want some kind of shuffle in that case, bitwise shuffle. Oh, it was for a machine learning idea. That's funny. I actually thought you meant 32 bits in, 32 bits out, and it would just shuffle. But yeah, okay, you mean 32-bit by 30 or 32 by 32 bit matrix, right? Oh, the bits of 32-bit, 32 integers at once. Now I see what you mean. I misread that totally. I misread that as like transpose the bits of a 32-bit integer at once. But now I understand what you mean. I don't know. Frankly, I think ideas like that are what machine learning needs, or at least what you can get away with in machine learning now. Like just crazier ideas. If you can find a way to compute that, or if you can find a nice way to compute actual models with that kind of like weird approaches, I think that's pretty valuable right now. Or at least we're trying, you know. I'm actually going to see what this looks like if I export it right now. I'm curious. Oh, it's pretty small, but it does look pretty good. I gotta be honest, I'm getting really bored of doing this right now, so I might do the rest of this later. Yes, exactly, Artemis. And back to Vliv, now we're back to the hardware unit I was discussing earlier, aren't we? Which is this dot product engine that I might do. I'm glad you're getting a healthy dose of Schadenfreude, Kratchev. There's definitely some things I wanted to add to this. I think because I need to add bit widths to a lot of these parts, for example. So I think I'm going to give myself some room. This sucked. There's that pain you were talking about. That's not too bad. I don't remember how I aligned this before, but whatever. I think it was like this. Maybe it was out of the middle like that. That's probably what it was. Yeah, I think that's what it was. Come on, snap where I want it to. There we go. Are you talking about Zachtronics, Artemis? That sounds like Zachtronics. And I love that they did that, if that's what you're talking about. Like with TIS 100 and Shenzhen IO. And I love Opus Magnum. That game is so much fun. Yeah, so the reason I removed this is because these are going to be 128 bits each, so each one of these is going to be 32 bits. I guess I also need some like room here to add these widths everywhere. Something like that. Actually, that's almost what I wanted, not quite. I wanted that, basically. Because then I'll be able to add some of those bit width ticks. I need them. So I want basically all of these parts to be 128 bits. And then this is going to be 32 bits, which is going to be kind of important. Oh, I heard Exapunks is so good, but I haven't checked it out at all. I need to do that. And they came out with that really dark one. When was that? Where you like make drugs. I haven't tried that one yet either. But I've heard good things about like all these. I actually want to do this. I'll do that. No. Where's my... I click to move. No. How about that? There we go. I think I also want to be cheeky about this. And like move this up. Okay, can I like hide this for a second? I guess I can just move it for a second. And then is this still clear? If I do like tab back. No, it was clear with how it was before. And that's important to note because these, the width here is going to be 32. No, yeah, 32. So I need some kind of like shift thing here. Because out of this is actually 64, so I need some way to reconcile that. Can make these. No, actually, that was probably better how they were. Okay. That went better than I expected. Yeah, I know what you mean. A lot of those papers are really dense and hard to read. A lot of graphics papers are like that too, but I find machine learning to be extra cryptic, to be honest. I find with a lot of that stuff, you just have to actually like take physical notes and like write things down on paper. At least for me, that helps a lot, because otherwise I just like, I'll start watching videos and I just won't retain any of it. And then that's not really useful anymore. I find the same is true with category theory, is something in particular that like whenever I look into it, I don't take rigorous enough notes, and then I just like never retain any of it. And that's something I want to get better at. That seems to be a trick that helps for me, at least. Just always take notes. Ferris talks about life hacks. Oh no. This is the kind of thing that like I would love to be able to like script this kind of document, but when I tried, like for example using dot and graph-viz, it was even worse, right? Like I ended up much preferring the ability to actually draw by hand. And at least this tool saves in a textual format. It doesn't seem to be that human readable though, so I don't know if we actually get the benefits of that, but I don't feel too bad dumping it into Git. All right, so this is where things are important here, because we get 64-bit results out of this. And again, maybe I give in and do floating point for all this, but right now I'm thinking this. So this product register is actually 128 bits wide. Yeah, same, two curves. And I even went back and like relearned a bunch of linear algebra stuff from a book like last November or whatever to brush up for some machine learning stuff at work. Yeah, very true, Artemis. Very true. I was kind of thinking to add like dotted lines over these registers. Oh, look, they even have places where I could snap to do that. Maybe not, because it'll just look bad with the labels. Yeah, I think this is fine, actually. So yeah, this register is actually double width, and that's why I took out the path to be able to read from that, which I had in an earlier version of this document. I guess with this thick line, there's no way to make these look super nice. That's fine. That's fine. Or maybe it's not. I don't know. I think I'm just going to live with it. Yeah, I think that's fine. So yeah, I need to do something about this. I was thinking about having like a barrel shifter. And the reason I wanted that is so you could do like a lot of the vertex transformation math in like 16.16, but then you could decide while you have this larger product, you could decide which bits you actually want on the output. And I also need to add some things down here, like we need to mux the reg to load zeros or ones, especially for the W component. And somewhere here, I want like to do clamp min max. If this is going to support lighting, then that's something we want around here. To do some kind of bit selection here. Actually, I don't know about this. I definitely want this to be 128, but I think this is going to end up being 32 or something. Whoops. Hey, Anna Marin. I definitely agree with that, Artemis. There's a lot of papers that feel like they didn't actually build what they said they built, or it just doesn't seem like it was substantial enough research to be useful. Like, it's a shit show. But I think that's true for any like papers in any field, especially one that's as popular as machine learning is right now. So I don't think it's a problem that's specific to machine learning. I just think it's extra obvious because of the sheer amount of papers that we see these days. That's not to say it doesn't suck, because it does suck. But yeah. That. And actually, I think there was one more thing I wanted to fix really quick related to docs. Oh, by the way, I don't know if I talked about this, but this is kind of some operations to accelerate. I did definitely talk about this in words, but I didn't show this list. Again, vertex position transformations, possibly even mat 4x3 by vec3. So the fourth is constant. And then I want to support these as well for lighting, which these would have worse occupancy, but they would still be pretty fast. They would be as fast as the 3-row 4-component multiplies. And again, lighting n.l, and then you need maybe a POW LUT or something. I might want that as well. Clipping and binning, yeah. All the things that this unit is ultimately going to be used for. definitely vertex transformations, maybe the other stuff too. We'll have to see. We'll have to see. In the meantime, back to what I was going to do in doc. We have... Oh, can this render SVG? No, it definitely cannot. Let's see. Memmap. I think I messed this up. Or maybe I fixed that. No, looks like I fixed it. I don't know if these are right, but that's fine. Whatever. Yeah, this is kind of all I feel like doing today. I don't really feel like doing more of this. So I think I'm going to go. I've been streaming for 2 hours anyway, so... Well, a little bit less because I started late, but anyway. Anyway, thanks guys for hanging out. Exactly, Artemis. I bet that paper exists. But yeah, thanks again, guys, and I'll see you next time.